Now, again, just to point out, we can move these vectors all around, and so go back to 2-dimension here. If I've got a vector that, let's say it starts here at 4, and I want to go, that one's 4, 1. Initial point at 4, 1, and so it goes up to so the initial point is 4, 1, and it goes up to 3, 5. Okay, that's a vector. Well, is there any difference between that vector and this vector? Starts at the origin and goes up to this 2, 1. Oh yeah, 1, 4, sorry. Just checking. All right. So we got the 1, 4 initial point. That's the same vector, isn't it? Because this is the same because it goes to the right 2 and then up 1, just like this one goes to the right. So any vector that we draw that's 2 units to the right, 1 unit up is equivalent to that vector. So we could come down here, say at -3, 2 units to the right, 1 unit up, same vector. Go back here, 2 units, 1 unit up. So any vector we could draw, kind of parallel or whatever you want to say. That one's not my best job there, but okay, a little better. Okay, there we go. I like that better. Is that bothering you? Okay. Now, with that in mind, here's they do have a couple of questions in the book about this. I wanted to give you. How do we? And we'll do this some. I believe we'll do this some later on too. How do we take a vector that's up here and then put it where it's at the origin? So we can put it in the, this would be, we could do this one in the, what's that point, 2, 1. We can put that in our vector notation. It's a lot easier to designate because we don't have to say, well, the initial point's here. How do we do that? Well, you think about it, we can get 2 and 1 out of these 2 points. How? You subtract. You subtract the so you subtract the initial quantities and subtract the terminal quantities, and that gives you your 0, 0 initial point vector. Okay. All right. So given A is x1, y1, and B is x2, y2, those 2 points. Then the vector AB can be represented by our 0 origin vector A, A1, A2. So that's initial point at the origin. Yeah. Just subtract the x's, subtract the x2 minus x1, comma, y2 minus y1. What we just said. Harder to write than it is to show, matter of fact. Mathematics, that's a lot of times true. Something's harder to write than it is to kind of visualize there. All right. Now, of course, we'll be interested in different things about vectors, adding them and so forth. But let's talk magnitude. Just a little bit. Okay. So we want the length of A in our vector format here. Like we said, length or distance, that's typically represented with either just two bars like that around the vector, or some places you'll see double bars, same thing, means magnitude. And yeah, I just want the length of that vector. So how do I get it? It's the square root of a1 squared plus a2 squared, right? Gives me my magnitude, the length. Why? Pythagorean theorem, yeah. Distance formula, Pythagorean theorem. Yeah, we're talking about an a1, a2. So here's a1, a2 out here. So that's my point. The vector then is that. So that length, well, if you look at it as a right triangle, that's a1, that's a2, and so that's the square root of those two squares combined, right? So it's really that easy. Nothing more to it. What about in 3 dimensions? You got A, then is A1, A2, A3. What's the magnitude of it? It's the square root of all the squares added together, yeah. Pretty nice. I mean, there's you have to go through, it's now a 3-dimensional Pythagorean theorem, if you will, but it works out very nicely, very nicely. And we'll utilize the magnitude, matter of fact, here in just a second for something else, but that's all you do. Just square that, square that, square that, add them together, then square root all that. And now, it is important to note here, this magnitude, we're back to a scalar quantity, right? It's just a number.